Hello everyone, welcome back to my channel. Today we are here to deal with the important derivation of chemical kinetics chapter. In next 10 minutes you are going to learn the easiest way of deriving the integrated equation for zero order. In our next video we will learn the first order reaction. Okay, now starting from question. The question may be stated as derive an expression for integrated rate equation for a zero order reaction, or suppose it may be also be asked as derive an velocity constant of a zero order reaction, or else it may be asked as derive an rate constant for zero order reaction. Okay, now let us start with our first step. Consider a zero order reaction. We will consider a reaction where the reactant is R, that's going to give product with time. Initially we will have the reactant R, that on with respect to time it will give us products. Now our second statement is according to rate law. You know the rate law. From that we can state that for zero order reaction, rate of the reaction is directly proportional to concentration of the reactant, or the big bracket gives you the concentration of the reactant to the power of 0. See, you can see here in zero order reaction is one in which rate is proportional to 0th power of the reactant concentration. See, you can see here that this is the reactant concentration to the power of 0. So this is a zero order reaction. In first order we will have rate proportional to the reactant concentration to the power of 1. Okay, moving forward. Now we are supposed to remove this proportionality constant with the constant term. Rate is equal to K into reactant concentration to the power of 0. The constant term here is K. Now we know anything to the power of 0 will give you 1, that's unity. So the above equation will form in this way. The rate is equal to the constant. Now K is the rate constant or velocity constant, the constant which we obtained from the rate law. The proportionality, by replacing the proportionality constant, is K. That K is nothing but a rate constant or a velocity constant. Now but also rate is equal to differentiation of reactant concentration with respect to time. Let me tell you what is that. Rate is nothing but a negative sign is because it is decreasing, and differentiation is nothing but the concentration of the reactant. The reactant concentration is negative, means decreasing with respect to time. We are differentiating R with respect to time, but the quantity is going on decreasing, so negative is indicated. Now we have rate in this form also, we got rate in this form also. Now substitute this and this equation is equal to this equation, that's nothing but minus of differentiation of reaction concentration with respect to time is equal to constant. Now rearranging this equation, rearranging in the sense nothing but take this dt to the other side, that gives you d into concentration, reaction concentration is equal to minus k, the negative side also taken to the negative also taken to the other side, minus k dt. This on integrating we need what is the reactant k, what is the reactant r here. So integrate this equation. On integrating we will get the reactant r, concentration of the reactant r is equal to minus kt plus I. You know, whenever we integrate any equation, we will add a particular concentration. It may be C, it may be I, anything. Now we got I as a constant here, but we need to know what is actually the I stands for. Now let us check out what I stands for. To get I, we need to know R or any two conditions from this equation, such that if we substitute that condition to this equation, that will give you the constant I. We know the condition where from the initial condition we know the initial condition is at t is equal to 0. When the reaction starts, the moment when reaction start, that initial condition is t is equal to 0. Here we have got t value at initial condition, and the initial concentration is R naught. Initial concentration to the naught, that's nothing represented as R naught. Now we have got two values, that is initial concentration we got and the initial time we got. Substitute these two in this equation and get I value. Now substituting, initial concentration of the reactant is nothing but big bracket of R naught is equal to minus constant into 0. The time is 0 plus the integration constant I. Now what is the value of I? This term vanishes, this term will vanish to 0. Now I is equal to initial concentration of R, that is reactant naught. Okay, we got I value from initial condition. Now this I value is substituted in this equation. Okay, now substitute this in 2. This is the 2. Substituting, the concentration of the reactant is equal to negative of Kt plus initial concentration of the reactant. There is no confusion, I guess. If you are arrived at this step, then almost 90% of the thing is done. Now rearrange is required. Take this term to here and this term to here. Kd is equal to initial concentration of the reactant minus the present concentration at T. At T in the sense at the given time is this. Now take the T to other side, that will give you the rate constant expression of 0th order. K is equal to R naught, that's initial concentration of the reactant minus R, that's the concentration of the reactant at that given time. The time is T. Okay, you can see here this is the linear equation, the equation of a straight line. Y is equal to mx plus c, c is constant. Now x is variable, in the place of x we have t which is also variable. Now in the place of y, sorry m, we know mx plus c. In the place of m you have k. So what is k? Is the slope is m is equal to minus k here. K has negative here, that in the sense the k is representing a negative slope. We have written that in graph format. You can see here slope is equal to negative of k. The graph is represented with the help of the concentration versus time t, concentration versus time t. You can see here initial condition is at starting from initial condition, we have the concentration R naught at the time is equal to 0, t is equal to 0, we have initial condition R naught. That's the condition where we took here to find I. That's the same thing is represented, and the slope is nothing but negative of rate constant k. This is something equal to y is equal to mx plus c. M is nothing but minus k, which is a negative slope. We got k, that is nothing but our velocity constant or rate constant. This is the graph. Okay, we have completed our derivation. What's the important step? The important step is to remember whole this derivation. Let me tell you some tips. Start with this basic concept. Basic concept is nothing but a reactants turns into product. If you came to know this, you will know that at the time is equal to 0, the concentration of the reactant is R naught. You will get this idea. Then you know this, the first equation is fetched from rate law, and the second equation is a general one, which is a differentiation of the concentration of the reactant. We will get first step, second step, third step. If you know all this, this is not a big thing, and at least you will be in a format where you can guess what going on in your derivation. At last you can write the concentration is equal to minus kt plus R naught. If you remember y is equal to mx plus c, at this time we will get to know the slope is negative k. Okay, we finished our derivation here. In our next video we will deal with the first order reaction equation, the integrated equation of first order reaction equation. Okay, now we have taken our time to reach you the concept, teach you the concept and reach you our teachings. So it's your time. Please do subscribe, share the video to your friends or who is learning this concept, so that we will be happy to see that many are watching our YouTube channel. So for now, thank you, bye.